Hi, so for today we're going to talk about integrating factors found by inspection or by integrable combinations. But before that, let me just have a shout out to my students in FEU Tech. Okay, hi. So please study now because your finals is fast approaching. And to Kalum Pati, a mechanical engineering student from Rizal Technological University. Hi, so happy viewing in our video, okay, for today. So let's get started. Integrating factors found by inspection. Usually, this topic is actually involves solving differential equation by actually having an integrable combination, just like our formulas right here. As you can see here, we have several derivatives here of certain function x and y. So for the first part, what are we going to do is to recognize this equations present in our differential equation if we want to solve the differential equation. So for example, the derivative of differential of xy is equal to this, wherein we use product rule here, okay? So that the differential of xy is x dy plus y dx, okay? And here, we use the quotient rule for x over y, okay? Low d high minus high d low over low squared, okay? So we have low multiplied by our high, okay, our numerator, we have y dx is equals minus, x dy over y squared, okay? And the same also for this, okay, such that the differential of y over x, simply we have x squared on the denominator while we have y squared here. And of course, the sign also changes, right? And for this, we have the differential of x squared plus y squared is equals to 2x dx plus 2y dy. So we are going to familiarize ourselves, no? We should be familiar with this because we are done already in differential calculus. Okay, so we need to identify this, or we at least want to make the differential equation look like this so that we can easily integrate the factor, okay, or the integrate the given the solution or the DE in order for us to come up with the correct solution. Okay, so let's get started. Okay, I suggest before we proceed, please copy this formula or take a picture of it, okay? So that as along the way we are going to solve the problems, you are actually having a copy of this. You have a copy of this formulas, okay? So for number one, let's get started. So how do we solve this by integrable combination? First, we need to actually uh, distribute. We have 2x y squared plus y dx minus x dy is equals to 0. And furthermore, we can simplify or we can distribute dx. So we have 2x y squared dx plus y dx minus x dy is equals to 0. So as you can see here, upon distributing y and dx term here, we have this differential equation. And as you can see here, this is familiar with us. Okay, this term is familiar with us. Okay, according to our formula a while ago. So this is actually what? A quotient rule. So that if we are going to divide this both sides by, okay, both sides by 1 over or y squared, such that we will be having what? We will be having 2x dx plus, okay, 1 over y squared of y dx minus x dy is now equal to 0. And if we are going to look at it, okay, that is equal to plus y dx minus x dy over y squared. So, again, why do we divide the whole term by y squared? Because we know, okay, that we can simplify this as simply equal to what? The differential of xy is simply equal to low d high y dx minus x dy over low squared. So, this term could be actually substituted by only by the differential of dx1. So we have 2x dx plus, okay, the differential of x over y over or equal to 0. Okay? So how do we find the differential equation from that. Okay? We need to eliminate the differentials, okay, dx and this the differential of x over y by integrating both sides of the equation. So here, upon integrating this, we have 2x squared over 2. So 2's will cancel. Plus, simply, when we do this, we are simply canceling out the differential operator or differential sign or d and the integral, so that we have x over y is equal to some sort of c. Okay? Because the differential or integral of constant could be any constant. So we have x squared plus x over y is equal to c. Furthermore, if we multiply this both sides by y, we have x squared y plus x is equals to cy. So that's how we solve by integrable combinations. First, we look for patterns in our equation, okay, by the differentials. And we're going to divide by means of dividing them by a variable, okay? Like what we did here, we divide both sides by y squared so that this equation or this term becomes this term, of which we can simply substitute the differential of x over y. And upon integrating, okay, upon integrating without any terms around here, okay, we can simplify this as simply x over y. So we have now the differential equation x squared, or the solution to the differential equation, as x squared y plus x is equals to cy. Okay, let's go now to our second example. Second example, quantity x minus y dy, okay, is equals to quantity x minus y dx. So the first thing to do is to distribute, okay, x dy minus y dy. Oops. Okay, I'm sorry. X dy minus y dy is equals to x dx minus y dx. Okay? So, from here, we can, what? We can actually group x dy. Okay, I would transpose this plus y dx. Okay, I'm gonna retain this x dx plus y dy. Okay, so what are we going to do here is simply we have the pattern for this. This is simply, okay, I'm trying, what I'm trying to say is that this is simply, okay, that is simply equal to d of xy. Okay, differential of xy, because we have dxy, okay, the product rule is x dy plus y dx. We cannot do this, what we did here, on the right side, because this doesn't have a pattern, okay, x dx plus y dy. This doesn't have a pattern. So we have differential of xy is equals to x dx plus y dy. If we are going to integrate both sides of the equation, okay, so what will happen? Simply, this would cancel. We will be left on the left side of the equation as xy, and we have x squared over 2 plus y squared over 2 plus c. And if we're going to rearrange this, multiply both sides by 2. Oops, that does not look multiply, but raised to 2. So multiply both sides by 2. So we have 2xy is now equal to x squared plus y squared plus c. Okay. Furthermore, if I'm going to transpose this on the left side or on the right side, we have x squared minus, okay, minus 2xy plus y squared. Okay, transpose the c. So negative c is still c. So we have the solution to the differential equation by integrable combination as this as our final answer. Okay, so x squared minus 2xy plus y squared. So you need to look for the patterns, or you need to look for the equation that would be equal to this or on our equations a while ago. Okay, so even if it means to divide both sides by a certain variable, just for you to arrive at that the same pattern, you can always simplify that as in our given formulas. Okay, for number 3, Okay, number 3 problem, we have x dy minus y dx equals to x raised to 4 y dy plus x cubed y squared dx. So the first thing that we're going to do here is to be observant. Okay, so on the left side of the equation, we have x dy minus y dx. What does that tell us? Okay, so this is really familiar with us as the differential. Okay, let's say the differential of, let's say, y over x is x dy minus y dx over x squared. So I need to divide the whole side of the equation by x squared, okay, so that this would be simply equal to the differential of y over x. But before that, okay, let me just simplify first. This. Okay, so because we might get another integrable combination on the right side of the equation. So if we are going to factor out x cubed and y, of course, so we have x dy plus y dx. Oh, and again, this is another pattern because the differential of xy, the product of xy, is simply x dy plus y dx. So that we can also replace this by the differential of xy later on. So if we divide both sides by 1 over x squared, as what I've said to you, okay, we need to divide it by x squared so that we can simplify this into the differential of y over x. So we have x dy minus y dx over x squared. Okay, on the left side or on the right side, this would be cancelled. So x squared would be cancelled. So we are left with xy here and x dy plus y dx here. Okay, so what will happen here is we can now substitute, okay, we can now substitute the this formula. Okay, so we have differential of y over x is equals to xy multiplied by the differential of xy. Okay, so what do we need to do? The very last step to obtain the solution to our D is to integrate both sides. So what will happen here? This would simply be equal to y over x. Okay, how do we integrate this? Notice that our integrand contains differential of xy. So meaning we can integrate in terms of xy. Okay, this integral would not be bothered, okay, because we have both x and y in our differential here. Okay, so unlike if that is dx, we can actually factor out y, okay, outside of the integral because that's considered as constant. Or if this is simply equal only to dy, we can factor out x outside of the integral. But the fact that this is differential of xy, we need to integrate this. This is not considered as constant, okay? So both of them are not considered as constant. So if we are going to let u as equal to xy and du to our differential xy, so we can have the integral of the u multiplied by du. And we know the integral of that. That is y over x is equals to u squared over 2 plus c. But again, u is equals to xy. So if we substitute it back, so we have xy squared over 2 plus c. So upon simplifying this, we have y over x is equals to x squared y squared over 2 plus c. If we cross multiply this, okay, if we multiply both sides by 2x such that I'm going to eliminate the denominator, so we have 2y is equals to x cubed y squared plus cx. So this is our solution for our differential equation by integrable combination. And again, going back to what I've said a while ago, we need to divide this by x squared because the most common problem encountered by the students is how will I know, okay, on what term I'm going to divide. Okay, what term I'm going to divide. Okay, is it x squared? Is it x? Is it y? Okay, it depends. Okay, on the given problem. Okay, so let's go now to problem number 4, wherein we have y dx plus x quantity x plus x cube y squared. This is cube. Okay, this is cube. So we have x cubed y squared dy is equals to 0. Okay, the very first thing that we're going to do here is again distribute, okay, the term dx and dy. So we have x dy plus x cubed y squared dy is equals to 0. As you can see here, we have a pattern again, such that we have this. Okay? So, this term is simply equal to what? Again, that's right, to the differential of xy plus x cubed y squared dy is equals to 0. Okay? So, as you can see here, if we integrate it, both sides, okay, so we have a constant here, x cubed, okay, with respect to y. So, what I'm going to do is to eliminate this x cubed such that also this term would have only a term that is purely in terms of y. Okay, so to do that, so I'm going to multiply both sides or divide both sides by x cubed, okay, y cubed. Why x cubed, y cubed? For me to cancel x cubed here, okay, y cubed, for me to have dy over y here. Because, okay, in order for me to differentiate this also again, I should have another term y. So, what will happen is that we have xy over x cubed y cubed, okay? So if I'm going to only to cancel x cubed here, I would be having a trouble in integrating this. So I put y cubed. Why y cubed? Because why not y squared? Okay? Why not y squared? Because to simplify the integration of this. So we have x cubed will cancel, y squared over y cubed will be dy over y is equals to 0. Okay? So that's the point. Okay, so we have to integrate both sides of the equation so that we have this. So the integral of, okay, I can rewrite x cubed y cubed. Okay, we can rewrite x cubed y cubed as x raised to cube. Okay, and if I'm going to bring this into the numerator, I can negate the exponent xy raised to negative 3 differential of xy. And this is simply ln of y. And this integral of constant or 0 is simply c or ln c. It's the same. Okay, it's still the same. So what will happen here? To integrate this, I could let u is equals to xy raised to negative 3. And our du would be the differential of xy. So that I can integrate that. So we have u raised to negative 3 du plus ln of y is equals to c or ln of c. So integrating this, we have u raised to negative 2 over negative 2. Okay? Plus ln of y is equals to c. And the u is simply x, y, okay? I mean, this is, we have to let u as x, y only, okay? So, x, y raised to negative 2 over negative 2. Okay, I'm so sorry, I made a mistake that we have to let u only x, y, not including the negative 3 exponents, okay? So, we have plus ln y is equals to c, and we have negative 1 half x squared y squared plus ln y is equals to c. So this must be our answer. Okay? Some books you would see the answer of c includes ln. ln of c or c, that is still the same. So that is our final answer. Okay, for our last problem, okay, we have this type of problem, okay, for our last problem, 2x dx, okay, plus 2y dy plus x squared y squared dx is equal to 0. So what will we do here? Again, 2x dx, okay, distribute, okay, the x squared y squared dx. So we have plus x squared dx plus y squared dx. Okay? As you can see here, okay, we have 2x dx, 2y dy. What does that tells us? Okay? That this is actually differential of x squared plus y squared. Okay? So we have 2x dx plus 2y dy. Okay? But before that, what are we going to do? I'm going to simply transpose first. Okay? Simply transpose first this. So we have negative x squared dx minus y squared dx is equals to 0 on the right side of the equation. Because if we are going to integrate that, okay, later on you will see how easy it is to integrate. Because this is 2x dx, we have 2y dy, so we have, I can factor out negative here, so we have x squared plus y squared. Now, here on the right side of the equation, dx. Okay? So if I'm going to divide both sides, okay, by x squared y squared, okay, just to eliminate the x squared y squared here, so we have x squared plus y squared. We will be having 2x dx plus 2y dy over x squared plus y squared is now equal to negative of dx. Why did I did that? Because actually, this is equal to the differential of x squared plus y squared, and this is over x squared plus y squared. So, if we are going to integrate both sides, first I'm going to substitute this, okay? Substitute this equal to uh, this to our differential. So we have differential of x squared plus y squared over x squared plus y squared is equals to negative dx. If we integrate both sides of the equation, okay, if we have, again, we let our u equal to x squared plus y squared, then our du is simply equal to the differential of x squared plus y squared. So what will happen in the integral now of du over u is equal now to the integral of negative dx. So what will happen here? This is ln of u is equals to negative x plus c. Okay? And ln of u, or u, is simply equal to u is x squared plus y squared is now equal to negative x plus c. If we exponentialize both sides of our equation, okay, so as to eliminate ln, okay, so as to eliminate ln, okay, we'll be having this equation wherein our natural logarithm sign would cancel. So this is equal still. Okay, so what will happen? We are left with x squared plus y squared, okay, is equal now to e raised to negative x multiplied by e raised to c. But e raised to c, okay, e raised to c is equal to c. So we can rewrite this as x squared plus y squared is equal to c e raised to negative x. Okay, and furthermore, we have x squared plus y squared is equals to, I can bring this down by negating its exponent. We have e raised to x. So that our answer is e raised to x multiplied by x squared plus y squared is now equal to c. So that is our final answer for this differential equation. Okay, so thank you so much for listening, and I hope you learned something from our video today all about integrable combinations in solving the differential equation or finding the integrating factors by inspection. So thank you so much for listening, and God bless.